All right, let's talk about one of the biggest, most exciting challenges in all of science right now. Actually building a quantum computer that can do something useful. Because it's not just about getting more power. It's about surviving this brutal gauntlet of problems that are blocking a total computing revolution. So, let's step inside.
So, you might be asking, why even bother with all this hassle? Well, the payoff is, it's almost hard to wrap your head around. The magic words are super polynomial speedup. Now, that doesn't just mean a little bit faster. Oh no, we're talking about solving a problem in minutes that would take our best supercomputers billions of years. It's like the difference between walking to the moon and just teleporting there. That's the kind of power we're talking about, the power to crack unbreakable codes or design new medicines atom by atom.
But of course, there's always a catch, right? And here it is. All of that mind-blowing power comes from wrangling the weird, super fragile laws of quantum mechanics. So the very thing that gives these machines their magic is also what makes them almost impossibly hard to build and control. It's basically a high-wire act 1,000 feet up with no safety net.
Okay, so let's get into the gauntlet. Challenge number 1, we have to master the quantum alphabet. See, in any computer, you have gates. You can think of them as the basic verbs, the fundamental commands that tell your bits what to do. But, and this is a big but, the quantum versions of these verbs play by a whole different rulebook.
And this right here shows you just how different that rulebook is. In your laptop, a normal classical gate, say an AND gate, is what we call irreversible. If the output is 0, you have no idea what the original inputs were. That information is just gone. Poof. Well, quantum mechanics just flat out forbids that. Every single thing you do to a qubit has to be reversible. You have to be able to rewind the tape and know exactly where you began. No information can ever be lost.
So let's meet a few of these quantum verbs. First up, we've got the Pauli-X gate. This one's pretty easy to grasp. It's basically the quantum version of a classic NOT gate. All it does is flip a qubit from 0 to 1, or from 1 back to 0. Super simple, totally essential. It's our most basic building block.
Okay, next up is the Hadamard gate. And this is where things get really weird and really powerful. The Hadamard is the superposition maker. It takes a qubit that's just a plain old 0 or a 1 and puts it into a state where it is both 0 times 1 at the exact same time. Yeah, you heard that right. This is one of the absolute cornerstones of quantum power.
And rounding out our starting lineup, we've got the CNOT, which stands for controlled knot. I like to call this one the entanglement engine. It takes two qubits and basically ties their fates together. The rule is simple. It will flip the second qubit, but only if the first qubit is a 1. It creates this spooky, deep connection between them, which is absolutely crucial for running the really complex algorithms.
Okay, so we have our alphabet. We've got the Pauli-X, the Hadamard, the CNOT. We can start stringing them together to make quantum sentences. But this brings us crashing into the second, and honestly, maybe the most frustrating challenge of all, the relentless pursuit of perfection.
See, it's not enough to just have these gates. They have to work perfectly, every single time, across maybe millions or even billions of operations. So, what happens if they don't? What happens if just one of those little gates makes one tiny mistake in the middle of a huge calculation?
Well, that's where this idea of gate fidelity comes into play. You can think of it like a report card or maybe a success rate for each one of our quantum verbs. It's a number, usually something like 99.9%, that tells you exactly how often the gate does its job perfectly and how often it messes up. And that tiny mess up can be absolutely disastrous. And this is what makes it so tough. I mean, 99.9% fidelity? That sounds amazing, right? A+. But think about it. If your quantum algorithm needs 1,000,000 operations, that tiny 0.1% chance of an error starts to add up fast. The errors just compound on each other, they create interference, and pretty soon they've completely overwhelmed the whole system. Your beautiful calculation just turns into random, meaningless noise.
And that relentless pile-up of noise, of errors, leads us directly to the third and final challenge in the gauntlet, what I'm calling the tyranny of depth. This is a huge architectural bottleneck, and it's where our first two problems, having the right gates and making them perfect, smash together into one giant engineering headache.
So first, what do we even mean by circuit depth? It's actually pretty simple. It's just the length of your quantum program. Think of it as the number of steps in your recipe. It's the total number of sequential time slots you need to get from the beginning of the calculation to the end. Now, you might be able to do 10 things at once in a single time step, but the depth, that's a measure of the longest single-file line of operations you have to get through.
And this right here shows you exactly why that's a bottleneck. If you have a shallow circuit, a short program with just a few steps, that tiny error rate doesn't have much time to mess things up. Your answer is probably going to be reliable. But the really world-changing algorithms, the ones we're all excited about, they need deep circuits with thousands, maybe millions of steps. And with the tech we have now, every single step adds a little more noise, a little more error, until the whole thing just falls apart. Our gates just aren't good enough yet to survive that long of a journey.
So there you have it. That's the gauntlet. First, you have to master the gates. Then you have to achieve almost impossible levels of perfection. And then you have to use that to build circuits deep enough to do something useful. This is the race. This is what thousands of brilliant scientists and engineers are working on right this second. These aren't just roadblocks. They're the absolute bleeding edge of quantum research. So let's just quickly recap the whole gauntlet, right? It's really 3 challenges all tangled up together. Number 1, gates. You got to have the right alphabet, the right verbs to manipulate qubits. Number 2, fidelity. You have to make those operations so close to perfect that they almost never make a mistake. And number 3, depth. You got to be able to string enough of those perfect operations together to run a long, complex program before the tiny errors that still exist can ruin everything. Every time you see a headline about a quantum breakthrough, a new kind of qubit, a better way to correct errors, it's really an attack on one of these 3 problems. They are, without a doubt, the 3 hardest puzzles in quantum computing today. Which leaves us with a really fascinating question, doesn't it? Which one of these massive challenges are we going to solve first? Because the answer to that is what's going to kick off the true quantum age.